Inside a magnetically confined fusion reactor, the plasma is under constant threat from edge-localized modes, violent bursts of energy causing sudden containment failures. To keep this chaos stable, we have to solve magnetohydrodynamic, or MHD, equations, alongside Vlasov-Maxwell differential equations. The Vlasov-Maxwell equations are mathematical models that describe the precise dynamics of collisionless plasmas interacting with electromagnetic fields in real time. Classical supercomputers calculate these variables sequentially. By the time they process the fluid dynamics of a single microsecond of turbulence, the physical plasma has already evolved and breached containment. Current approaches use reinforcement learning to react to these changes, adjusting magnetic coils thousands of times a second on reactors like the TCV tokamak. But reacting is still too slow. We require a predictive control system with absolute zero latency. Achieving stable, net positive fusion requires a computational architecture that operates natively at the exact speed and complexity of the physical chaos it tries to control. The proposed solution is the dimensional Braid engine, a cyber-physical quantum topological processor. Instead of abstracting math through traditional silicon logic gates, the engine functions as a digital twin. It uses physical quantum phenomena to directly model macroscopic classical chaos. Standard superconducting qubits cannot survive the extreme electromagnetic noise and radiation adjacent to a fusion reactor environment. They require extreme isolation to maintain their states. The dimensional Braid engine bypasses this fragility by integrating 5 distinct, fault-tolerant exotic phases of matter into a single continuous feedback loop. The first module is the logic core, built on topological quantum computing. It relies on Majorana zero modes. These are exotic non-abelian anyons, quasiparticles that act as their own antiparticles, which store quantum information non-locally across a degenerate ground state. A degenerate ground state means the system has multiple distinct configurations that all share the exact same lowest possible energy level. Logical operations are executed by braiding these anyons. Exchanging Majoranas yields a unitary rotation, linking their topological path to the resulting logical state. Because information is encoded in the braid's global topology, local thermal noise only vibrates the particles. It cannot unknot the computation. Braiding Majorana fermions provides an intrinsically error-immune logic framework, complex operations adjacent to reactors without losing data. The second module handles data storage using fracton-based error-resilient quantum memory, specifically utilizing a framework called Haas cubic code. In standard 2D surface codes, an error excitation can hop along a string of adjacent qubits, rapidly spreading decoherence throughout the system. Haas code relies on type 2 fracton topological orders. Here, elementary error excitations, called fractons, are created in pairs but remain strictly immobile. Causing a logical flip requires a coordinated, highly non-local operation matching a self-similar fractal pattern. The rigid geometry physically obstructs error propagation. This lack of string-like logical operators essentially creates a quantum hard drive. It passively protects the engine's running plasma state variables from decoherence over extended durations. The third module drives synchronization using a Floquet time crystal. Coordinating millions of Majorana braiding operations and fracton memory checks requires a precise global clock. That clock cannot risk being desynchronized by external thermal noise. A discrete time crystal is an exotic, non-equilibrium quantum phase that explicitly breaks time translation symmetry, oscillating continuously without absorbing any net energy from its environment. By periodically driving a localized many-body system with a specific period, say t, the observables self-organize. They begin to oscillate at a subharmonic frequency of precisely nt. This data plot illustrates the empirical proof. It shows a single logical z-operator wave oscillating perfectly between +1 and -1 at that doubled period, while the local single-qubit measurements beneath it remain flat and unaffected by noise. This topologically ordered time crystal acts as an indestructible metronome, ensuring every spatial layer of the engine operates on a perfectly phase-coherent schedule. The fourth module is the data ingestion layer. holographic field encoding via ADS-CFT-inspired tensor networks. The ADS-CFT correspondence is a theoretical mapping that translates a gravitational theory within a 3D volume of space into a quantum field theory on its 2D boundary. Translating the continuous, massive, three-dimensional magnetic topology of an entire tokamak plasma into the discrete qubit registers of the engine presents a scaling challenge. The holographic principle solves this by entirely and redundantly encoding information from a three-dimensional bulk volume onto its two-dimensional boundary. It implements this using a happy, perfect tensor network, creating an exact isometric embedding directly from the bulk to the boundary surface. To process this data efficiently, the engine applies parafact tensor decompositions. This mathematical technique splits high-dimensional data into low-rank representations, isolating the fundamental symmetry modes of the plasma. Holographic encoding compresses billions of variables into protected logical operators, enabling the engine to process the reactor state exponentially faster than classical models. The final module brings the entire system into a closed physical loop, real-time fusion plasma feedback control. The continuous cycle works like this. Physical sensor data hits the holographic boundary and is secured in the Fracton memory. It is then processed via time-synchronized Majorana braids, outputting optimized magnetic coil currents back to the reactor. Because the tensor-compressed MHD simulations run faster than real-time, the engine possesses a predictive advantage. It calculates and applies stabilizing magnetic fields before physical instabilities can materialize in the plasma. The engine scales to physical reality, outputting its commands to the massive auxiliary coils and perturbation fields of a commercial reactor. This closed-loop system shifts fusion reactor control away from reactive classical methods and entirely into predictive, topological quantum mechanics. The ultimate benchmark of this architecture is maintaining a deeply ignited, perfectly stable plasma state within a narrow, uncorrupted topological corridor. Current classical fusion efficiency limits struggle to confidently breach the break-even point, where energy output simply matches energy input. By completely eliminating edge instabilities, the reactor can operate continuously at extreme pressures. This naturally leads to the hypothesis that topological control could yield up to a 1,000-fold net energy gain. While an integrated engine is highly visionary, every single subsystem, from Majorana zero-bias peaks to holographic wormhole simulations on Google's Sycamore processor, is grounded in peer-reviewed empirical evidence. The dimensional Braid engine provides a practical blueprint for using the fundamental topological math of the universe to physically sculpt reality.